There. That's the voice of Bill Coates, who was, I'm told, Bryson's predecessor in the guy who actually makes his lectures work, you understand. In fact, I met him. I gave one of these discourses 35 years ago, and he looked after me in the same way that Bryson is looking after me this evening. Now these are essentially the same machine, except that this one it's made of soft metal. Wax works a lot better. They have a property which is important to a biologist, and I'll come back to it in a moment, that they work both ways. We've shown it as taking the information out of the groove and turning it into sound. But if you shout like anything down there, you can cut the groove. I mean, that's how you get the information into the groove, right? So it works both ways. So does that one. You can shout down there and make a pattern on the wax. And that's how you make the pattern on the wax. Later, the thing became rather more refined, and we have here I won't say exactly a modern gramophone, but at least you don't have to wind it up. I mean, my first gramophone wound up, but this one, let's have a listen. Is run by electricity, by something like that. Yeah. Okay, it's now saleable, marketable, makes lots of money. But it's different from these other two in the following way. You can shout at that thing until you're blue at the face and you won't cut a record. Okay? This is a piece of information transducing machinery which transduces information in only one direction. Now, why does that matter? Well, I'll come to that in a moment. I just want you to remember those two bits of machinery. But to go back to biology, genetics is essentially the science about how information is stored and transmitted between generations. Developmental biology is the science of how that information is translated from one form to another during development, so that you finish up with fingers and ears and eyes and hair and stuff like that. And evolution, which is my own subject, is really the science of how the information gets into the animal in the first place. But they're all basically about information. Now, the first person to understand that, rather surprisingly, and I discovered that reading him quite recently, was writing, like the machine, towards the end of the last century, not in this one, and it was the great German biologist, August Weismann. You'll know of Weismann, I'm sure, that he argued that acquired characters are not inherited. That is, that if you develop great big muscles, the blacksmith develops great big muscles, this doesn't mean that his children will have great big muscles unless they also exercise. And we all know that that's what he said. What is less well known, I think, is why he thought it. The essential reason why he believed it to be true is that he could not understand how it could work. He couldn't understand how the information, I've got big muscles, could be translated into some kind of chemical message in the sperm so that it would cause the child to have big muscles. Now, you may say, how do I know that that's what he was thinking? Well, essentially because he said so. In his big work he wrote towards the end of his life, The Theory of Evolution, he wrote it in German, but I don't read German, I can only give you the English translation. He wrote, if one came across a case of the inheritance of an acquired character, it would be as if a man was to send a telegram to China and it arrived translated into Chinese. I think it's one of the most astonishing sentences in the 19th century. He understands, by the telegram analogy, that he's talking about information, and he knows that the reason why acquired characters are not inherited is essentially the reason which was given a chemical meaning by Watson and Crick in the central dogma of molecular biology, that you can't, that the machinery for translating information works only one way. It resembles this gramophone, which is a machine for transducing information from a groove into a sound, It won't enable you to change a sound into a groove, and it doesn't resemble these two pieces of apparatus, which will translate information in either direction. So, in a sense, Weissman's statement about the non-inheritance of acquired characters is not a statement like saying you can't have a perpetual motion machine, or the speaker cannot now levitate. I mean, those are universal truths, even of this speaker. Their statement more of the kind that this particular piece of apparatus, as it exists in our bodies, doesn't work in both directions. Now, I said that everything depends ultimately upon the replication of nucleic acids. How far do we understand the origin of this process? Well, not by any means completely. Let me describe an experiment some years ago now by my friend Leslie Orgel, in which he started with a solution with the different nucleotides, the 4 nucleotides in solution, and he seeded it with a really boring RNA molecule consisting simply of a string of Cs. And he got out an RNA molecule in which, well, he got out the original RNA molecule and paired against the Cs G nucleotides. Except every now and then, about once in 10 or once in 20 times, the wrong one, a U, and then back to G again. We're getting complementary base pairing. Chemistry gives us that for free, in a sense. That is just chemistry. It doesn't explain the origin of the first replicating molecules, really for, I think, 3 reasons. First, it doesn't explain where the units came from, and these units are not among the easiest of molecules to imagine how they could be synthesized in the absence of living organisms in the primitive soup. Amino acids are fine. You know, you can make lots of amino acids without any organisms around to make them for you, just by shining sparks through the medium, but you don't get nucleotides all that easily. Secondly, it doesn't tell you how to zip the stuff together when you've made it, and that's presenting chemists with some difficulties, I think. The problem that worries me more than those two, because those are problems, they're real problems, but they're problems for chemists, certainly not problems for me. The real problem is the one of accuracy. You do make about 1 mistake in every 10 or 20 replications, whereas in your cells and mine, the rate of error is about 1 in 1,000 million, which is quite good, quite precise. How do you get from 1 in 10 or 20 to 1 in 1,000 million? Well, you get it by using enzymes. Among other things, you get it by proofreading, which depends upon enzymes and so on. What are enzymes? Enzymes are proteins. Enzymes are strings of amino acids. And this led to a very real problem. I mean, some of you may have been worried already, I hope you were worried by the fact that I talked loosely about RNA carrying a message, carrying information, and you may have said to yourself, well, it's all right saying that, but information means that it has a meaning. What is the meaning of this message? If it's just a message that replicates without having a meaning, it's not interesting. It isn't really information. Well, the meaning of an RNA molecule, the meaning is the protein that it codes for. The notion of a code, of course, also goes back to the early part of the last century. Here is a coding device invented, my wife tells me, actually in 1830 or thereabouts. The Morse code, and those of you who know Morse code will know that that is RI, or Royal Institution. So it works. It'll code things. In just the same sense that is the code for Royal Institution, or RI, so particular sequences of nucleic acids are the code for particular kinds of proteins. And I want to spend the next quarter of an hour or so asking how that could possibly have come about.